A star 500 light-years away is dying, and nobody can predict when it will kill itself. It is massive enough to swallow our star along with every planet that orbits it, all the way out past Jupiter. Astronomers recently found it has a hidden companion buried inside its own outer atmosphere, possibly accelerating the collapse. When this star goes, it will release a pulse of neutrinos so enormous that our detectors will catch it before the light does. We will trace every stage of that death. Meet the stars scientists consider even more dangerous, and find out what the machines buried underground are waiting to hear. If you enjoy this channel, subscribe. Prepare yourselves. We begin. There is a star in the shoulder of Orion that has been burning for 10 million years, and every piece of evidence we have suggests it is almost done. It marks the left shoulder of one of the most recognizable constellations in the winter sky. And for most of human history, it looked like any other bright star. Steady, reddish-orange. Sailors used it to navigate. Farmers knew when to plant by its position. Ancient Egyptians tracked it alongside the Nile floods. Countless generations looked up and saw permanence. What they were actually looking at was one of the most extreme objects within a few hundred light-years of Earth, hurtling toward one of the most violent events the universe produces. Betelgeuse is a red supergiant. To call it large would be like calling an ocean wet. If you placed it at the center of our solar system, replacing our own star, its surface would reach out past Mercury, past Venus, past Earth, past Mars, and engulf Jupiter. Everything in the inner solar system, including this planet, would be swallowed inside a single star's atmosphere. Its diameter stretches roughly 4 times the distance between our star and Jupiter. Astronomers have directly imaged its surface, something almost no other star is close enough to allow, and what they saw was not a calm, steady sphere. It was a churning, boiling surface of enormous convective cells, superheated plasma the size of entire planets rising and falling in slow, violent waves. The star is roughly 16 to 19 times more massive than our own star, but it has burned through its fuel at a ferocious rate. Where our star has been calmly fusing hydrogen for 4.5 billion years and has another 5 billion to go, Betelgeuse has been running at full throttle. 10 million years old, and already dying. Its luminosity blazes between 100,000 and 150,000 times that of our star, most of it pouring into the infrared, which is why it glows that characteristic orange-red rather than white or blue. Astronomers at universities around the world have spent decades studying its spectrum, measuring its pulsation periods, analyzing its oscillations. A team at the University of Tokyo ran those measurements through stellar evolution models in a landmark paper published in June of 2023. Their conclusion, stated carefully and precisely, was that Betelgeuse appeared to be in the carbon-burning phase of its life, or possibly further along. They called it, in the restrained language scientists use, a good candidate for the next galactic supernova. That phrasing carries a weight worth sitting with. Every element lighter than carbon still has fuel to burn in stages above it. Silicon burns in days. Oxygen burns in months. Carbon has been burning for thousands of years. Somewhere inside Betelgeuse right now, in a core far too dense and hot for any human frame of reference, the clock is running. The star will explode. There is no scientific uncertainty about this outcome, only about the timing, which could be anywhere from a few hundred to a few tens of thousands of years from now. In stellar terms, that is not the future. That is now. For most of the time since humans began keeping records, Betelgeuse simply sat there and burned. It varied slightly in brightness, as all large stars do, cycling over roughly 400 days through a gentle brightening and dimming. Astronomers catalogued this and moved on. Then, in the autumn of 2019, something changed. Betelgeuse had always varied. So when its brightness dropped slightly below normal, most observers filed it under routine behavior. But by November, the drop was larger than expected, and ultraviolet measurements from the Hubble Space Telescope were already showing something unusual. The chromosphere, the hot outer atmosphere just above the visible surface, was flooding with dense outflowing plasma. Material was moving away from the star faster than the normal stellar wind, in quantities that registered clearly across the star's entire ultraviolet emission spectrum. By December, ground-based telescopes in Chile, equipped with adaptive optics, were getting images of Betelgeuse's actual disk, something most stars are too far away to resolve, and what those images showed was unlike anything previously recorded. The star was not just dimmer, it was asymmetric. January brought worse numbers. The brightness kept falling. By mid-February of 2020, Betelgeuse had dimmed from its typical magnitude of around half to a magnitude of roughly 1.7, a threefold drop in apparent brightness, the faintest it had been in all of modern recorded history. Orion looked wrong. Anyone who had spent years watching the winter sky noticed immediately that something was off about the familiar constellation's left shoulder. The internet caught fire. Amateur astronomers flooded forums with measurements. Professional observatories redirected telescope time. The coverage on general news sites reached people who had never once thought about stellar physics because the framing was irresistible. Betelgeuse might be about to explode. Every few years, a new science story captures that particular mix of the vast and the viscerally personal, the sense that something enormous and cosmic might be about to happen within our lifetimes. This was one of those moments, and for several weeks in early 2020, millions of people were genuinely watching a star to see if it would die. Professional astronomers were more cautious. They knew the star's history of variability. They knew the timescales of stellar evolution, and most of them suspected there was an explanation short of imminent supernova. Several pointed out that a star in the final seconds of silicon burning would give no visible warning. Betelgeuse could simply go dark one night and explode the next morning, with no dimming cycle necessary as a precursor. The Great Dimming, happening slowly over weeks, was in some ways more consistent with a large-scale atmospheric event than with core collapse. They were right about that. But the explanation they eventually pieced together was almost as strange as the supernova hypothesis. In its own way, the full picture took months of analysis from multiple observatories, a combination of ultraviolet spectroscopy, infrared photometry, polarimetric observations, and high-resolution imaging. When the story finally came together, it involved two separate events happening in rapid sequence, each one rare, each one unusual, and together producing something nobody had ever watched unfold in real time on a star. And the imaging at the heart of the discovery came from a telescope in Chile, pointing at a star 500 or more light-years away, and somehow showing, with enough clarity to shake the field, that the southern half of Betelgeuse had simply gone dark. When the Very Large Telescope in Chile pointed its adaptive optics camera at Betelgeuse in December of 2019, the images that came back were striking enough that the team that produced them spent months checking their work before publishing. The star's disk, tiny even for this telescope given its distance, was divided in a way that made the scientists look twice. The northern hemisphere glowed normally, orange and steady. The southern hemisphere had gone almost entirely dark. A clear, sharp boundary ran across the face of the star, separating the bright half from the part that had effectively switched off. To understand what made this so unusual, you need to appreciate what you are looking at when you see Betelgeuse as a disk rather than a point. The star's apparent size in the sky, even at 500 or more light-years, is just large enough for specialized instruments to resolve features on its surface. Its diameter is so immense that the distance across its visible face represents several times the gap between our star and Jupiter. An object that size, dimmed so dramatically and so specifically in its southern half, was telling a story. The question was, what story? The team that published the imaging results in the journal Nature in 2021, led by researcher Miguel Montajes, had been watching Betelgeuse for years. Their data showed that before the southern dimming, the southern hemisphere had also experienced a measurable temperature drop. The photosphere in that region had cooled by roughly 200 Kelvin relative to normal, consistent with a large, cool patch like an enormous version of a sunspot. But the temperature drop alone was not enough to explain the full dimming. When other researchers ran the numbers, they found that even accounting for the cool patch, something else was reducing the light even further. Something opaque was positioned between the star's southern face and our instruments. Infrared measurements offered the critical clue. While the visible brightness of Betelgeuse plummeted, its infrared brightness fell by a far smaller margin. In a star, visible light and infrared light are both generated by the same hot photosphere, and they should drop together if the star itself dims. They were separating here, which meant the visible light was being absorbed and re-emitted at longer wavelengths. Dust absorbs visible light very efficiently and radiates the absorbed energy back as infrared heat. Something dusty had formed in the line of sight between us and the southern face of Betelgeuse, a foreign cloud positioned just above the star's surface in the surrounding space. Polarimetric observations confirmed the scattering signature of dust particles. The directional alignment of the light coming from the star's southern hemisphere bore the distinctive pattern of radiation scattered by small solid grains rather than emitted directly from a hot surface. Several independent groups reached the same conclusion at roughly the same time. A dust cloud had formed between us and the star directly in front of its southern hemisphere, blocking a substantial fraction of its visible face. The mystery of where that cloud came from and how it had materialized in a matter of weeks above the surface of a star pointed to something even more dramatic happening just below the visible surface. The full explanation arrived from two directions at once. Ultraviolet observations from the Hubble Space Telescope, taken in November of 2019, just before the peak dimming, had recorded something extraordinary in the chromosphere above the star's surface. The emission lines that scientists use to measure outflowing material showed plasma moving outward at roughly 6 kilometers per second, far faster than Betelgeuse's normal stellar wind. The outflow was not gradual. The spectral signatures indicated that a massive quantity of material had been rapidly ejected from somewhere below the photosphere and was now racing outward through the chromosphere into space. Later, detailed hydrodynamic simulations produced by a team led by researcher Morgan McLeod reconstructed what had happened. Somewhere beneath the visible surface of Betelgeuse, a convective cell had erupted. This is not unusual in itself. Betelgeuse's interior is in constant violent motion, giant bubbles of superheated plasma rising from the deep interior toward the surface. And Betelgeuse is known to have convective cells so large they would dwarf most solar system objects. What made the 2019 event different was scale. The bubble that erupted in early 2019 was, by the estimates derived from the simulations, roughly the size of Jupiter, a mass of plasma comparable to several times. Jupiter's total mass was ejected from the photosphere outward into the chromosphere and then into space. This is technically called a surface mass ejection, a stellar-scale version of the coronal mass ejections our own star produces. But where our star's ejections carry perhaps a few billion tons of material at most, Betelgeuse's event expelled something in the range of multiple Jupiter masses. The ejected gas was initially hot enough to glow, but as it expanded outward and away from the star's intense radiation, it cooled. At a certain temperature, silicate compounds in the gas reached their condensation point, and solid dust grains formed. The cloud of newly condensed dust expanded over the following weeks, reaching a size large enough to cover a significant fraction of the star's southern face as seen from Earth. Observers on the ground watched the southern hemisphere darken without knowing they were watching freshly formed dust settle into place in real time. By April of 2020, the dust had dispersed enough for normal brightness to return. The star recovered, but something in its interior had been permanently disturbed. The normal 400-day pulsation cycle that Betelgeuse had maintained for as long as anyone had measured it was broken. After the event, the star's rhythm had shifted to a shorter period, the telltale sign that a shock had disrupted its internal structure. Then, in an unexpected turn, Betelgeuse went in the other direction. By April of 2023, it brightened to a magnitude of roughly 0.1, among the brightest it had been in decades. The pendulum had swung. The star that had faded below naked eye expectation was now blazing more intensely than almost any recorded measurement in recent history. A star that had dimmed dramatically and then recovered was now outshining its own normal range in the other direction. Betelgeuse had survived something unprecedented in the observational record, and the aftermath raised a question that would take several more years to answer. Something had triggered that convective eruption. The question was what? The hint had been hiding in the data for years. Betelgeuse does not vary on just one timescale. Alongside the 400-day pulsation cycle, there is a longer oscillation running roughly every 2,200 days, close to 6 years, that brightens and dims the star on a slower rhythm. Astronomers had known about this cycle for decades, but its cause had resisted explanation. Pulsation models could account for the shorter period. The longer one was simply called the long secondary period, a name that essentially admitted the field had no idea what was producing it. In 2024, 2 independent research groups looked at this cycle with fresh eyes. A team led by Jared Goldberg and another led by Morgan McLeod applied radial velocity analysis to Betelgeuse's historical brightness and motion data. Both groups reached the same conclusion. The 6-year cycle did not look like a pulsation. Its characteristics matched the signature of orbital motion. Something was orbiting Betelgeuse and gravitationally tugging at its outer atmosphere on a roughly 6-year schedule. On December 9th of 2024, astronomers pointed the Alopece instrument on the Gemini North telescope at Betelgeuse. The detection that came back was tentative but real, a faint object approximately 6 magnitudes dimmer than the star itself, positioned at the expected orbital distance. A companion had been directly imaged for the first time. By July of 2025, a full confirmation paper appeared, carrying a remarkable set of findings. The companion is a young star similar to our own in mass and age, orbiting inside the extended outer atmosphere of Betelgeuse on a roughly 6-year path. The team at Carnegie Mellon University that led the analysis nicknamed it Beetle Buddy, and the name stuck. Its orbit is nearly edge-on to our line of sight, meaning every 6 years it plunges through the red supergiant's outer atmosphere and gravitationally stirs its layers from the inside. The implications are still being worked out. The companion's orbital period matches the long secondary period precisely. Its most recent close pass to Betelgeuse's surface, around 2018 to 2019, aligns with the timing of the Great Dimming. The gravitational disruption from a star-sized object dragging through Betelgeuse's outer layers may have churned the convective zone just enough to trigger the surface mass ejection that darkened the southern hemisphere. The companion that nobody knew existed may have been the hand behind the event that captivated the world. That discovery also changes the endgame. A red supergiant with a companion living inside its own atmosphere will not explode in the way stellar models assumed. When Betelgeuse's core eventually collapses, the expanding shockwave will interact with the companion's gravity, its orbital wake, the gas it has disturbed in the outer atmosphere. The companion itself may be ejected at high velocity. It may spiral inward and merge with the collapsing remnant. It may fundamentally alter the shape of the explosion, causing the blast to emerge more strongly in one direction than another. Every stellar evolution model ever built for Betelgeuse assumed it was alone. It is not alone. What happens when that companion is still there when the core collapses is a question stellar physicists are now actively working through. And to understand why it matters, you need to understand what is happening inside Betelgeuse right now, layer by layer. In the furnace, it cannot sustain forever. The interior of a massive dying star is nothing like what most people picture when they think of a star. The popular image is of something simple, a sphere of gas fusing hydrogen into helium, producing light and heat. That is accurate for most of a star's life. A massive star spends the vast majority of its existence in exactly that state, calm and stable on a human timescale. The hydrogen burning is steady, self-regulating, a vast nuclear reaction balanced against gravity in an equilibrium that can last for millions of years without significant change. But when the core hydrogen runs out, the simplicity ends, and a sequence of events begins that grows progressively more extreme with each step, accelerating toward a conclusion that nothing in human experience quite prepares you for. When hydrogen is exhausted in the core of a star like Betelgeuse, gravity contracts the core until the temperature climbs high enough to ignite helium fusion. The hydrogen burning does not stop. It moves to a shell around the helium-burning core and continues there. The star now has a layered structure, 2 active burning zones at different depths, each running at different temperatures and pressures. Then the helium in the core runs out. The same sequence repeats. Carbon fusion ignites at a still higher temperature in the core, helium burning shifts to a shell around it, and hydrogen burning continues above that. Each new fuel requires higher temperatures to ignite and burns at a faster rate. By the time a star is near the end of this process, its interior has become a nested series of shells, each one burning a different element. From the outside in, hydrogen, helium, carbon, neon, oxygen, silicon. Each layer is fusing the element below it, generating energy in progressively diminishing amounts as the reactions become less energetically favorable. At the center is the accumulated product of silicon burning, the element that ends everything. The critical feature of this sequence is the timescale. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands. Carbon burning, a few thousand years. Neon burning, a year. Oxygen burning, months. Silicon burning, days. Each stage burns faster than the last by orders of magnitude, because each successive fuel is harder to ignite, requires higher temperatures, and releases less energy per reaction. The star is burning faster and getting less for it each time. Based on the pulsation period analysis published in 2023, Betelgeuse appears to be somewhere in carbon burning, or possibly further along. If the star has reached oxygen or silicon burning, the remaining time before catastrophe can be measured in years or less. This is what the clock looks like from the inside, a steady acceleration, each stage arriving faster and faster than the last, until the final stage arrives almost instantaneously by comparison with everything that came before. The star has lived for 10 million years in gradual decline. The final weeks, if they are close, will arrive like a door slamming shut. And the next element, waiting at the bottom of that chain, is the one the universe uses to build walls. At the peak of nuclear binding energy sits iron. This matters for reasons that go straight to the heart of why stars can exist at all. Nuclear fusion releases energy when lighter elements are forced together to form heavier ones, because the resulting nucleus is more tightly bound than the ones that went into it. The binding energy per particle increases as you climb from hydrogen through helium, carbon, oxygen, silicon. Each step produces energy because the product is more stable than the ingredients. This released energy is what pushes outward against the crushing weight of the star's own mass, keeping the layers above it from collapsing inward. Fusion is what holds a star up. Iron does not fuse with any energy advantage. When silicon burning produces iron at the core, the element that forms is sitting at the peak of the binding energy curve. There is no heavier element it can fuse with that would release more energy than it consumes. Fusing iron costs energy rather than producing it. Every previous fuel bought the star more time by releasing energy as it burned. Iron offers nothing. The fusion process that has powered Betelgeuse for 10 million years can progress no further, and the entire architecture holding the star against gravity has no foundation left to stand on. As silicon burning feeds more iron into the core, something called electron degeneracy pressure holds it up temporarily. Electrons, governed by quantum mechanical rules that forbid two of them from occupying the same state, resist compression with a pressure that has nothing to do with temperature. As long as the iron core remains below roughly 1.4 times the mass of our star, the electrons can hold the weight. This threshold has a name: the Chandrasekhar mass limit. Once the iron core grows past it, electron degeneracy pressure is overcome. There is no physical mechanism remaining to resist gravity. At that moment, the iron core begins to fall inward. Electrons and protons in the collapsing material are forced together by the increasing pressure, combining to form neutrons and releasing a flood of neutrinos. The gamma rays produced by the intense heat begin to tear iron nuclei apart, undoing thousands of years of silicon burning in seconds. This process consumes energy, making the collapse accelerate. The entire iron core, originally the size of Earth, compresses toward its fate in less than a heartbeat. Everything above the iron core, the oxygen shells, the carbon shells, the hydrogen envelope stretching out for hundreds of millions of miles, has no idea what has just happened underneath it. The outer star is still fusing, still glowing, still carrying the light of its surface out into the galaxy. The information that the core has collapsed travels at the speed of light, and the outer layers are far enough away that it will take time to reach them. For a brief window, the most massive explosion in light years is happening inside a star that still looks completely normal from the outside. The star that has spent 10 million years resisting this moment can no longer resist. Gravity has been patient. And as the core falls, a question hangs over everything. At these distances, are we safe? The distance to Betelgeuse is not precisely known, and the reason is one of the more peculiar stories in modern astronomy. Measuring a star's distance normally uses parallax. The apparent shift in a star's position as Earth orbits our star provides a measurable angle that translates directly into distance. The technique works well for most stars. Betelgeuse is an exception because of its own size. The star's surface is not a smooth, steady sphere. It is a roiling mass of giant convective cells, each one moving and shifting, causing the photocenter, the apparent center of the star's brightness, to wander by measurable amounts. When the parallax signal you are trying to measure is small enough that the photocenter's wandering competes with the shift itself, your measurement becomes clouded by the star's own behavior. Betelgeuse is so large it is almost too large to measure accurately using standard techniques. Multiple research groups over the past 2 decades have arrived at estimates ranging from about 500 to 700 light-years. The best current estimate, derived from stellar evolution modeling combined with pulsation analysis, places Betelgeuse at roughly 550 light-years. This is genuinely uncertain enough to matter when calculating what will happen when the star explodes. And here is what will happen when it does. The explosion, traveling outward from the collapsed core, will reach Betelgeuse's surface within hours. The shock will break through into space, and the initial radiation pulse will reach Earth traveling at the speed of light. When it arrives, 550 or more years after the explosion itself, observers on Earth at night will see a point of blazing light appear in Orion that was not there an hour before. Within a day, that point will have brightened to rival the full moon. It will be visible in daylight. It will cast shadows at night. Estimates of the peak brightness range from roughly magnitude -10 to -13, comfortably brighter than the full moon at the upper end of that range. Historical supernovae at far greater distances gave us a reference. A supernova roughly 8,000 light-years away in the year 1006 reached -7 and was visible during the day for weeks. Betelgeuse is 10 times closer than that star was. The brightness ratio scales as the square of the distance. The arithmetic is striking. For several weeks, Betelgeuse will blaze in the sky as one of the strangest objects any living human has ever witnessed. A star appearing in a constellation that has looked the same since the first city was built. Then it will slowly fade, over months and eventually years, leaving behind first a visible nebula and eventually, over human generations, an expanding cloud of glowing gas marking the grave of the star that for 10 million years marked the hunter's shoulder. The cosmic ray flux reaching Earth will increase slightly, but remain far below any harmful threshold. The distance that makes Betelgeuse interesting rather than terrifying is its greatest gift to this planet. At 550 light-years or more, the explosion is a spectacle, one of the greatest our species will ever witness. But spectacle is all it is. The mechanism that will produce it is another matter. Because the physics of what happens inside the iron core in the final second before the explosion is something that borders on impossible to fully comprehend. The collapse of the iron core is one of the fastest and most violent events in the observable universe, and it happens inside an object you could drive across in a few hours. The iron core, as it reaches the Chandrasekhar limit and begins to fall inward, is about the size of Earth, roughly 8,000 miles across. In the final fractions of a second, it is accelerating under its own gravity, which means it is accelerating under the gravity of roughly 1.5 times the mass of our star. Focused into an ever-shrinking sphere, the infall velocity reaches roughly a quarter of the speed of light. In less than 1 second, an object the size of Earth is compressed into a sphere roughly 30 kilometers across, about the size of a city, sitting somewhere below the surface of the remaining star. The density of that sphere exceeds anything that exists anywhere else in the observable universe, with the sole exception of other neutron stars and black holes. A single teaspoon of the material at the center of that collapse would outweigh a mountain range on Earth. To put that another way, the entire mass of a star is now occupying a volume you could walk across in under an hour, assuming the temperature were somehow not in the hundreds of billions of degrees and the gravity were not instantly lethal at any conceivable distance. What forms in that compressed sphere is a proto-neutron star, and it is unlike any object a human brain was designed to picture. Its crust will eventually be a layer of crystalline iron 1/2 mile thick. Inside that crust, the material is so dense that individual protons and electrons have been forced to merge into neutrons. The atoms that made up the iron core no longer exist. The particles that made up the atoms no longer exist as atoms. What remains is a vast sea of subatomic material packed so tightly that quantum mechanics is the only thing keeping it from compressing further. The compression does not stop gradually. It hits a wall. When the collapsing matter reaches the density of atomic nuclei, the strong nuclear force, which at ordinary distances is attractive and holds nuclei together, becomes repulsive. The core rebounds. In the language of physics, this is the nuclear bounce. The infalling material, traveling at a quarter of the speed of light, slams into the newly formed neutron star and rebounds outward in a pressure wave. The outward moving pressure wave is the beginning of the supernova explosion, but only the beginning, and a fragile one. The shockwave that the bounce generates immediately faces resistance from the enormous quantities of material still falling inward above it. It begins to slow. Whether it survives to reach the surface of the star and explode it, or stalls and collapses back inward, depends on events in the chaos behind the shock front. And those events are powered by something so abundant and so elusive that for decades, scientists could not decide whether to be amazed or terrified by what it implied. At the moment the core bounces, two things happen in the same instant. The shock wave begins its outward push, and the newly formed proto-neutron star, screaming with temperature in the trillions of degrees, begins releasing energy at a rate that makes every other energy source in the observable universe look modest. Neutrinos are generated inside the collapsing core at a rate that is genuinely difficult to frame in human terms. These are particles that interact almost not at all with ordinary matter. Trillions of them pass through your body every second, generated by our own star and traveling through Earth as if it were not there. They are the most abundant, massive particles in the universe, and the most reluctant to interact with anything. In the first 10 seconds after the core bounce, the proto-neutron star generates roughly 10 to the power of 58 of them, a number so far beyond any human intuition that specific quantities stop helping. The clearer way to think about it is this. The energy carried by those neutrinos in those 10 seconds exceeds the total light energy our star will radiate across its entire 10 billion year lifetime. That is where the real power of a supernova lives. All of the visible brightness, the weeks-long blaze seen from Earth, the expanding shell of gas that glows for centuries in a nebula, the X-rays, the gamma rays, all of it combined represents roughly 1% of the total energy released. The other 99% leaves as neutrinos before the explosion even begins. The light show that would turn Betelgeuse into a second moon is the leftovers. On February 23rd of 1987, a star in a satellite galaxy about 168,000 light-years from Earth collapsed and exploded. The neutrino burst from that collapse arrived at 3 separate underground detectors on 3 separate continents. The detectors, named Kamiokande in Japan, the Irvine, Michigan Brookhaven detector in the United States, and Baksan in Russia, had been built for entirely different purposes. They were looking for protons decaying, a prediction of grand unified theories that turned out to be wrong. Instead, they found something far more astonishing. Roughly 25 neutrinos registered across all 3 detectors in a 13-second window. The numbers were small, but the coincidence across 3 independent instruments on opposite sides of the planet made the signal unmistakable. The visible light from the explosion arrived 20 minutes later. For the first time in history, science had caught the core collapse in the act, confirming that the theory was right. Neutrinos come first, light comes second, and the gap between them tells you how long it took the shockwave to reach the surface. The universe had handed physics a perfect confirmation, wrapped in a star's final moments. A supernova generated roughly 10 to the power of 58 neutrinos, and 3 detectors on Earth collectively caught 25 of them. Given the distances involved and the extraordinarily small probability of any individual neutrino interacting with ordinary matter, the number matched the theoretical prediction almost exactly. The universe had done the experiment and the model had passed. But the shockwave itself was about to reveal the deepest problem in all of stellar physics. For roughly 30 years, between the 1960s and the early 2000s, physicists could not make supernovae explode. This is worth sitting with, because the gap between what they knew and what their models could produce was embarrassing enough that the field had a running joke about it. Everyone agreed that supernovae happened. The night sky had the remnants to prove it. The Crab Nebula, the expanding shell of gas and a pulsar spinning 30 times per second at its center, was the direct remnant of a supernova that Chinese astronomers watched in the year 1054. The evidence was abundant and unambiguous. The problem was that the simulations could not reproduce the event that created it. The shockwave produced by the nuclear bounce was supposed to travel outward through the remaining stellar material and blast the star apart. In one-dimensional simulations, meaning models that assumed the star was perfectly spherical and symmetric in all directions, the shock launched fine. Then it stalled. Around 100 to 150 kilometers from the center, the shockwave ran out of momentum. 2 things were draining it. As the shock moved outward, it ran into iron nuclei in the infalling material. The energetic shock tore those nuclei apart in a process called photodisintegration, spending vast amounts of energy to undo the nuclear structure that silicon burning had built over thousands of years. Every iron nucleus it encountered cost the shock a significant fraction of its driving force. Simultaneously, the shock was losing additional energy to neutrinos escaping from the hot region behind it. The combined drain was too great. In every one-dimensional simulation, the shock stalled and sat there at roughly 100 or so kilometers, gradually accreting more in falling material, growing heavier and heavier, while the theoretical star waited silently to collapse into a black hole. No explosion. Every attempt, the same result. A generation of physicists spent careers refining the input parameters, improving the neutrino transport physics, adding more detailed microphysics, and the shock stalled every time. Meanwhile, real supernovae kept happening in galaxies across the observable universe, obviously not consulting the textbooks. The field knew the core theory had to be correct, because the 1987 supernova had validated the neutrino burst. Something was missing from the models. The question was, what? And it took computational power that did not exist until the late 1990s and early 2000s to finally reveal the answer. Physicists began to wonder whether the missing ingredient was something fundamentally non-spherical. Real stars are not perfectly symmetric. They rotate. They convect. They have temperature differences across their surfaces. A perfectly spherical supernova is a mathematical convenience, and possibly a false one. Every assumption of perfect symmetry might be hiding the very mechanism that made the explosions work, but testing that hypothesis required simulating a three-dimensional collapse in enough detail to resolve the turbulent, chaotic region behind the stalled shock, and the computers capable of doing that did not yet exist. The solution, when it came, required throwing out the assumption of symmetry entirely and building simulations in full 3 dimensions. And what those 3-dimensional models revealed about the chaos behind the stalled shock changed the field completely. When researchers finally built the computing power to run full 3-dimensional supernova simulations, they found chaos behind the stalled shock where the 1-dimensional models had seen nothing unusual. In a perfectly spherical model, the region between the neutron star and the shock front is relatively orderly. Neutrinos pour outward from the neutron star surface. The shocked material sits in a roughly stable layer, and the system just sits there, not exploding. In 3 dimensions, that picture collapses almost immediately. The first thing that happens is convection. Neutrinos, streaming off the proto-neutron star, heat the material directly above its surface unevenly. Some pockets of gas absorb more neutrino energy than their neighbors and become buoyant, rising upward toward the shock. Cooler material above them sinks back through the gaps. A churning exchange begins, with heated plumes rising and cold fingers of gas descending, much like what happens in a pot of water heating over a flame, but operating at billions of degrees inside one of the most violent environments the universe produces. This convective motion has an important effect. It keeps heated material in contact with the neutron star's neutrino flux for longer before that material reaches the shock. More time in the heating zone means more energy absorbed. More energy absorbed means the stalled shock eventually has more support. The second discovery was something physicists had not predicted and could only see in 3-dimensional simulations. The stalled shock, rather than sitting still and accreting mass evenly, develops a large-scale asymmetric oscillation. The entire shock structure begins to slosh, tilting and spiraling as if it were liquid in a spinning container. Physicists studying this behavior gave it a formal name: the standing accretion shock instability. The shock is a pressure boundary between infalling material above and heated, neutrino-energized material below. When it becomes asymmetric, one side can bulge outward while the other pulls inward. The whole structure spirals and precesses, sloshing over timescales of tens to hundreds of milliseconds. This sloshing matters enormously. In a static, spherical shock, neutrino energy can only reach material sitting directly between the neutron star and the shock at a given moment. In a sloshing, precessing shock, the geometry constantly changes. Material that was outside the heating zone gets swept into it. Fresh, cooler gas replaces material that has already absorbed its share and absorbs more in turn. The efficiency of the whole system improves dramatically compared to what a symmetric model ever predicted. The two effects combined, convection churning the material and the instability sloshing the shock, finally gave the simulations the energy budget they needed. The revived shock, now carrying enough neutrino-deposited energy to push outward against the ram pressure of infalling material, begins to accelerate. The acceleration is lopsided. The three-dimensional models produce explosions that break out faster in some directions than others. The neutron star recoils in the opposite direction from the strongest part of the blast. The whole event is asymmetric in ways one-dimensional models never predicted. And this asymmetry turned out to match what astronomers actually observe in supernova remnants, where the expanding shells are almost never perfectly round. What the three-dimensional simulations also revealed, almost as a side effect of solving the explosion problem, was something extraordinary about what happens in the chaotic, neutron-rich material pouring off the neutron star surface in the explosion's first seconds. Because the dying star does not only release energy in those moments, it manufactures something, and the product of that manufacturing process is something you have almost certainly worn on your hand. As the revived shock tears outward through the remaining stellar layers, the neutron star at the center does not simply sit still and cool. It continues for several seconds to radiate an intense wind off its surface, a flood of particles and energy that rolls outward into the turbulent region behind the expanding shock. This wind is unique in the universe for what it contains and what it makes possible. The material leaving the neutron star's surface is extraordinarily rich in free neutrons, the same particles found inside every atomic nucleus, now available in quantities almost nowhere else in space can match. In that intensely neutron-rich environment, atomic nuclei begin to be built in ways no ordinary stellar fusion process can accomplish. The process is called rapid neutron capture. In ordinary stellar fusion, nuclei absorb neutrons occasionally, building up slowly through stable isotopes. If an unstable isotope forms, it decays before absorbing another neutron, and the chain cannot continue past certain mass limits. The heavy elements, the ones beyond iron that ordinary fusion cannot reach, simply do not form in that regime. But in the environment behind a supernova shock, the neutron density is so staggering that nuclei absorb neutrons faster than they can decay. An unstable isotope does not have time to fall apart before another neutron smashes into it and adds to the nucleus. The chain runs upward through masses and atomic numbers that no ordinary stellar interior ever reaches. A seed nucleus, perhaps an iron atom produced in the supernova's own burning shells, sits in this neutron flood and begins to absorb particles one after another. In a fraction of a second, it climbs from iron upward through elements that barely have names in common experience. When the neutron environment finally relaxes and the unstable isotopes begin to decay, they cascade down toward the stable elements that sit at each atomic number. Those stable elements include gold, they include platinum, they include uranium. Every gold atom in every ring ever placed on a hand, every platinum atom in every catalytic converter, every uranium atom ever split in a reactor was assembled in this neutron-rich wind in the seconds immediately following a stellar core collapse. This is confirmed, not theoretical. In August of 2017, the Laser Interferometer Gravitational Wave Observatory and Virgo gravitational wave detectors picked up the merger of two neutron stars in a galaxy about 130 million light-years away. The light from that merger, called a kilonova, showed spectroscopic signatures that matched rapid neutron capture products exactly. Astronomers watching the event estimated it produced an amount of gold several times the mass of Earth, forged in a millisecond collision and scattered into space. Supernovae and neutron star mergers are both confirmed sites where the same fundamental process builds the heaviest elements. Every gold ring on Earth carries atoms, assembled in events like these, swept up into a molecular cloud over billions of years, collapsed into a solar system, sorted into rock and metal, and eventually into human civilization. The violence of stellar death is the precondition for the chemistry of life on this planet, upstream of everything. The proof that all of this actually happens as the models predicted came from a real star in a satellite galaxy just beyond the Milky Way on an evening in February of 1987, when 3 underground detectors on 3 separate continents registered the same signal from the same direction within seconds of each other. On the evening of February 23, 1987, an astronomer named Ian Shelton was doing routine maintenance at the Las Campanas Observatory in Chile. He was checking photographic plates of the Large Magellanic Cloud, a satellite galaxy about 168,000 light-years from Earth. Something in the images was wrong. A new point of light had appeared where none had been the previous night. Shelton stepped outside to check with his own eyes and saw it immediately. A star that had not existed in any previous image, already bright enough to see without a telescope. He ran to tell his colleagues. An astronomer in New Zealand named Albert Jones independently spotted the new star the same night, confirming the discovery from the other side of the southern hemisphere. Within hours, word had spread to observatories across 2 continents. What Shelton found that night was the supernova, now designated supernova 1987A, the closest stellar explosion since Kepler's supernova in 1604. And for the first time in history, astronomers had instruments ready that could look beyond the visible light. 3 separate neutrino detectors were running underground on 2 continents. The Kamiokande facility in Japan had 1,200 tons of ultra-pure water surrounded by photomultiplier tubes. The Irvine, Michigan Brookhaven detector in Ohio held 8,000 tons of water in a salt mine. The Baksun Neutrino Observatory, buried under a mountain in Russia's Caucasus Range, had a liquid scintillator tank. All 3 had been built primarily to search for proton decay, a prediction of theoretical physics that had not been confirmed. They had never detected a supernova. They were about to. At 7:35 Universal Time, the detectors registered something. Kamiokande recorded 11 events. Irvine, Michigan Brookhaven recorded 8. Baksun recorded 5. 24 events total across 3 independent detectors in 3 countries, spread across a 13-second window. The timestamps aligned. The coincidence was impossible to attribute to random background noise. The detectors had caught the neutrino burst from a collapsing stellar core. The visible light from the actual explosion arrived roughly 20 minutes later. The neutrinos had come first, exactly as the theory predicted. The proto-neutron star formed instantly, released its neutrinos immediately. And those particles traveled through the entire star and across 168,000 light-years of space, arriving at the detectors while the shockwave was still fighting its way through the outer stellar envelope. The gap between neutrino arrival and optical brightening told researchers directly how large the progenitor star had been. The numbers matched. One more surprise waited in the archive photographs. The progenitor, identified as a blue supergiant rather than the red giant theorists expected, forced a revision to models that had predicted red giants as the primary sources of core collapse. Supernova 1987A went on to become the most studied astronomical event in modern history. Its expanding shockwave has now been running for nearly 4 decades, slamming into the circumstellar ring of gas the progenitor ejected thousands of years before its death. Chandra, Hubble, and eventually the James Webb Space Telescope tracked the collision brightening in X-rays, visible light, and infrared, watching an explosion's aftermath evolve in real time at distances close enough to resolve real structure. The remnant became a living laboratory for supernova physics, still producing new results. And what the combined picture established with clarity is that the energy of a stellar collapse is real, enormous, and capable of sending signals across the galaxy. With that established, the next question is the one that actually matters for any planet sitting in the vicinity of a dying star. How close is too close? The assumption most people carry about supernovae is that they are events happening somewhere else, vast and terrible and completely irrelevant to a small rocky planet at a safe distance. This assumption is reasonable for most stellar explosions in the observable universe, which are happening at distances measured in millions of light years. It is less reasonable for events occurring within our own galaxy, where the nearest stars are measured in hundreds or thousands of light years. And it becomes worth questioning actively when you look at geological records showing what happened to Earth a few million years ago. In 2023, a team of researchers led by Ian Brunton at the University of Illinois published a study analyzing X-ray observations of 31 real supernovae from multiple space telescopes, including Chandra, Swift, and the X-ray Multi-Mirror Newton Observatory. Their goal was not theoretical. They were measuring actual X-ray emission from actual supernovae at a range of distances and environments, then using those measurements to calculate how far away a supernova would need to be to damage the ozone layer of a planet like Earth. The results produced a number worth knowing precisely. Most supernovae are dangerous within about 25 to 50 light-years for direct radiation. At those distances, gamma rays and immediate radiation from the explosion would cause severe ozone destruction, but the study identified a more dangerous category: supernovae that explode inside dense clouds of surrounding gas ejected by the dying star before it collapsed. When the supernova shockwave slams into that surrounding material, the collision produces brilliant X-ray emission that persists for years or even decades rather than weeks. These interacting supernovae stay dangerous longer and at much greater distances. For the most X-ray, luminous interacting supernovae in the study, the calculated danger zone extended to roughly 160 light-years. At that distance, sustained X-ray bombardment would be sufficient to drive significant ozone destruction in a planet's atmosphere. 160 light-years is far enough to feel comfortable. It is not empty. There are hundreds of stars within that radius. And over the course of this galaxy's history, some of them were massive enough to explode. Earth carries the evidence directly. In oceanic crust layers deposited roughly 2 to 3 million years ago, and again around 6 million years ago, geologists have found elevated concentrations of iron-60, a radioactive isotope produced in supernovae but by no terrestrial process. These isotope layers persist across multiple ocean basins on opposite sides of the planet, consistent with a roughly uniform fallout pattern that rules out any local source. The candidate explosions are estimated to have occurred within a few hundred light-years. Some researchers have looked at fossil records from the same time windows and found elevated extinction rates among marine species living in shallow waters most exposed to ultraviolet radiation. The connection between the supernova evidence and the extinction data has not reached consensus, but the supernova events themselves are now well established in the geological record. Earth is not a passive bystander in a calm corner of space. It orbits inside a galaxy that produces catastrophic explosions on timescales shorter than its own geological history. Most of those explosions are too far away to matter. Some, historically, have left their marks. Understanding exactly how a distant stellar explosion becomes a threat to a planet's surface requires looking at a specific layer of atmosphere that most life on Earth takes entirely for granted. The ozone layer is not a thick shield. At its densest point, roughly 15 to 30 kilometers above the surface, the concentration of ozone molecules is still tiny by any ordinary measure. If all the ozone in the atmosphere were compressed to sea level pressure, it would form a layer only about 3 millimeters thick. This thin distribution of molecules blocks nearly all of the ultraviolet B and ultraviolet C radiation that our star continuously fires toward Earth. Without it, the surface of this planet would be chemically incompatible with most of the life currently here. When high-energy radiation from an external source reaches Earth's upper atmosphere, the consequences play out through chemistry rather than through direct exposure. The radiation triggers reactions in atmospheric molecules that then do the damage. X-rays and gamma rays colliding with nitrogen and oxygen molecules in the upper atmosphere do not simply pass through or bounce back. They ionize those molecules, knocking electrons loose and creating highly reactive fragments that would not otherwise exist in significant quantities. The ionization of nitrogen in particular produces nitrogen oxides, reactive compounds, that catalytically destroy ozone in a chain reaction, producing far more destruction than the original ionization event would suggest. Here is how the chain works. A single nitrogen oxide molecule reacts with an ozone molecule, pulling off one of ozone's 3 oxygen atoms and leaving ordinary oxygen in its place. The nitrogen oxide molecule, now briefly carrying the extra oxygen atom, collides with another oxygen molecule and releases that oxygen back, regenerating itself. One nitrogen oxide molecule can destroy thousands of ozone molecules before anything stops the cycle. This is the same chemistry that first alarmed scientists studying chlorofluorocarbons in the atmosphere, and it is the mechanism that makes external radiation events dangerous at distances where the radiation itself is not directly lethal. A sustained flood of X-rays from an interacting supernova, lasting years or decades, drives this chemistry continuously. The ozone layer, always under natural stresses from cosmic rays and solar variability, faces a burden that its self-repair mechanisms cannot keep up with. Globally averaged ozone concentrations can drop by 25 to 50% in the most severe scenarios modeled by researchers. Some regions, particularly at high latitudes where the damaged chemistry concentrates, may see far greater losses. The secondary effect compounds the damage. As nitrogen oxides accumulate in the lower atmosphere, they contribute to a reddish-brown haze that scatters and absorbs incoming sunlight. The surface darkens and cools. Agriculture faces a combination of increased ultraviolet radiation reaching the surface through the thinned ozone and reduced overall sunlight from the haze. Phytoplankton, which anchor the ocean food chain and produce a significant fraction of Earth's oxygen, are among the most ultraviolet-sensitive organisms alive. Marine ecosystems are particularly vulnerable for a reason easy to miss. Life in the ocean's upper layers has co-evolved with the ultraviolet filtering the ozone layer provides. The organisms living at the ocean surface never had to develop significant ultraviolet protection because it was never necessary. When that protection disappears, the organisms never adapted to handle the radiation, bear the brunt of the change. The weapon here is invisible and indirect. A star exploding 100 or more light-years away does not send a shockwave to this planet. It sends radiation that rewrites atmospheric chemistry, and the atmosphere becomes the mechanism of harm. The trigger is the radiation. The fuse is the ozone, and the consequences play out over years, across ecosystems that had no warning. With that chemistry understood, the safety calculation for Betelgeuse becomes precise, and the answer it produces is almost a relief. At 550 light-years, Betelgeuse is safe. The kill zone established by the Brunton study for even the most X-ray luminous interacting supernovae tops out at roughly 160 light-years. Betelgeuse sits 3 to 4 times beyond that threshold, comfortably removed from any scenario in which its explosion could meaningfully affect atmospheric chemistry on Earth. When it finally goes, the ozone layer will be fine. The biology of this planet will be fine. The only things affected will be the night sky and the careers of neutrino physicists, who will spend years analyzing one of the most data-rich stellar events ever recorded at such proximity. But the Brunton study's most important contribution was not confirming that Betelgeuse is harmless. It was establishing the numbers precisely enough to ask a harder question. How often, over Earth's 4.5 billion-year history, has a supernova occurred close enough to do damage? If the dangerous zone extends to 160 light-years, and if our galaxy produces on average 1 or 2 supernovae per century spread across its star-forming regions, some fraction of those events will fall within that radius over geological timescales. The mathematics of that question points toward a frequency that is uncomfortably non-negligible. Over the course of Earth's existence, the solar system has moved through different regions of the galaxy, sometimes passing closer to active star-forming areas, where massive stars are more common. The probability of a nearby supernova was higher during some of those passages than it is today, and the geological record may preserve the evidence of multiple such transits. The geological evidence makes that calculation concrete. The iron-60 deposits in oceanic crust, identified in multiple studies over the past 2 decades, represent real events, actual supernovae close enough to rain their ejecta onto this planet. The deposits at 2 to 3 million years ago appear in seafloor core samples from multiple ocean basins on different sides of Earth, consistent with a roughly uniform fallout pattern ruling out any local terrestrial source. The candidate stellar explosion is estimated to have occurred within a few hundred light-years. Some researchers have looked at the fossil record from the same time window and found elevated extinction rates among certain marine species, particularly shallow water organisms, most exposed to ultraviolet radiation. The connection between the supernova evidence and the extinction data is still debated and has not reached consensus. What has reached consensus is that the supernova event happened, and that it was close enough to leave physical evidence persisting millions of years later. Earth is not a passive bystander in a calm corner of space. It orbits inside a galaxy that produces catastrophic explosions on timescales shorter than its own geological history. Most of those explosions are too far away to matter. Some, historically, have not been. The record of which events came close enough to leave marks has only become readable in recent decades as geochemical techniques became precise enough to detect trace isotopes deposited across millions of years of geological time. The picture emerging from this detective work suggests Earth's history includes at least a few encounters with nearby stellar violence, encounters that may have shaped the long arc of life in ways scientists are only beginning to trace. The next nearest candidate for a genuinely dangerous event is a different star entirely, one that makes Betelgeuse look almost modest by comparison. It sits roughly 7,500 light-years from Earth in the southern sky. For a brief period in 1843, anyone living in the southern hemisphere could read by its light without any other source of illumination, and the star survived what produced that light. In the year 1677, Edmund Halley catalogued a star in the southern constellation Carinae. He recorded it as a 5th magnitude object, barely visible to the naked eye, unremarkable in a sky full of brighter stars. Nothing in that catalogue entry suggested Halley was looking at one of the most violent objects in the Milky Way. Over the following century and a half, the star showed occasional brightening but nothing alarming. Then the 1830s began, and it started to climb. By 1842, it had become brighter than any star in the southern sky except Sirius. In 1843, it peaked. Observers across the southern hemisphere reported that the object, now known as Eta Carinae, had reached an apparent magnitude of roughly -0.8, making it the second brightest star in the entire sky. From Cape Town to Sydney to Montevideo, it blazed overhead, bright enough to be seen in daylight, bright enough to read by on a clear night. Unlike a supernova, which flares and fades in weeks to months, this blaze persisted. It held for years. Then it faded, slowly at first, then more steeply over the following decades. By the 1890s, it had dimmed below naked eye visibility entirely. By the 20th century, it required a telescope to see it all, and here is the thing that confounded astronomers as they began to study its history. A star producing light comparable to a supernova for years had survived. What actually happened during those decades is still being reconstructed, but the broad picture is now clearer. Eta Carinae ejected a staggering quantity of mass over a roughly 20-year period surrounding the 1843 peak. Estimates range from 10 to 40 times the mass of our star expelled in the form of gas and dust. A typical core collapse supernova throws off only a few stellar masses of material in a single event lasting seconds. Eta Carinae surpassed that total mass output without dying, without collapsing, without producing the neutrino burst that a real stellar death requires. Something different had happened. Astronomers reached for a new term. The event was a great eruption, and the star was called a supernova imposter, an object that mimics the visual appearance of stellar death without actually completing it. The star had tapped into an energy release mechanism capable of producing supernova-level luminosities without triggering collapse. The leading hypothesis involves the star operating at or above the Eddington luminosity, the theoretical maximum brightness where radiation pressure from the star's own light equals or exceeds gravity's inward pull, causing the outer layers to be blown away rather than held in place. What makes Eta Carinae unique is the object itself. It contains approximately 100 to 150 times the mass of our star in a single blazing sphere, 5 million times as luminous, hovering at temperatures between 9,000 and 35,000 Kelvin depending on its current state. It is, by most measures, close to the largest star that can exist without being immediately destroyed by its own light. It has been fighting this limit for as long as it has existed, and the Great Eruption was what happens when a star of this mass momentarily crosses the line. It survived. It is still there, and the structure it left behind in 1843 contains details about Eta Carinae's interior that no direct observation of the star itself could reveal. The debris ejected during the Great Eruption did not disperse evenly into space. It took shape. What formed in the decades after 1843 was a double-lobed structure, two opposing bulges of dense gas expanding outward from the star along its polar axis, creating an hourglass silhouette roughly half a light-year from lobe tip to lobe tip. When Hubble imaged it in detail, the result was one of the most striking photographs in the telescope's history. A pair of glowing orange-yellow lobes pinched together at the center, surrounding a star so bright it still saturated the detector even with the nebula in frame. Astronomers called it the Homunculus Nebula. The name means little man in Latin, chosen because the original lower-resolution images suggested a vaguely human silhouette. The structure is expanding at over 2 million kilometers per hour, and it has been doing so continuously since the 1840s. At that velocity, it has reached a size that light itself would take roughly half a year to cross. The chemical composition of the homunculus is what makes it scientifically extraordinary. Spectroscopic analysis of the nebula's gas shows it is rich in nitrogen and helium and depleted in oxygen and carbon. This particular combination carries an unmistakable signature. It is material that spent a long time in the hot inner regions of a massive star, processed through the carbon-nitrogen-oxygen cycle of hydrogen burning. The gas in the homunculus was once deep inside Eta Carinae, cycling through the nuclear furnace, and the Great Eruption launched it directly into space. The homunculus is a window into the star's interior, a glimpse at chemistry happening beneath the photosphere, written in expelled gas across half a light year. Nested inside the main homunculus is a second, smaller structure, the little homunculus, formed during a lesser eruption in the 1890s. The two concentric structures, one inside the other, record two separate episodes of violence. Each eruption left its signature in surrounding material, and the whole assembly is a layered archive of Eta Carinae's recent history. A 2015 study proposed that the Great Eruption may have had a more complex origin than a single star misbehaving. Researchers Simon Portuguese-Zwart and Edward van den Heuvel suggested that Eta Carinae was originally a triple star system, that two of the three stars merged around 1838, and that the combined mass and energy of that merger, combined with orbital interaction with what is now the companion star, triggered the main eruption in 1843. Under this model, the star at the center of the homunculus today contains the remnant mass of three original stars fused into one object. That would explain the extremity. It may have started enormous, then been made more enormous still by a merger. Since the Great Eruption, Eta Carinae has not been quiet. A second eruption in the 1890s produced the little homunculus. By 2003 and 2004, the star's X-ray brightness doubled unexpectedly. Over the past century, it has steadily brightened from invisible to the naked eye to a magnitude of roughly 4, faintly detectable without optical aid under good conditions. The structure of the homunculus lobes tells researchers one more thing that becomes critical when assessing this system as a future threat. The lobes extend outward along the star's rotational axis. That axis points in a direction that astronomers have looked at carefully and with undisguised concern. Betelgeuse will produce a spectacular supernova, Eta Carinae. When it finally collapses, has the ingredients to produce something categorically different in almost every dimension. The distinction is not a matter of degree. It is a matter of physics producing fundamentally different outcomes, and the specific combination of circumstances surrounding Eta Carinae makes it the system that keeps astronomers genuinely uneasy in ways Betelgeuse does not. Begin with mass. Betelgeuse contains roughly 16 to 19 times the mass of our star. This is certainly enough to produce a core collapse supernova, which requires a minimum of about 8 solar masses. Eta Carinae holds 100 to 150 solar masses in a single object, even after expelling tens of solar masses during the Great Eruption. A collapse of that much mass under gravity produces a fundamentally more energetic event. Simulations suggest the most massive stellar collapses can release 10 to 100 times more energy than a standard core collapse supernova. These events are sometimes called hypernovae, and they are associated with the most extreme stellar explosions observed in distant galaxies. The second factor is the dense circumstellar environment. Betelgeuse is surrounded by material from its stellar winds, but nothing as concentrated as what encircles Eta Carinae. The homunculus nebula contains 12 or more solar masses of material positioned directly around the star. When a supernova shockwave from Eta Carinae's eventual collapse slams into that surrounding gas, the collision will produce X-ray emission of extraordinary brightness and longevity. This is precisely the scenario the Brunton study identified as maximally dangerous, an interacting supernova, where the shockwave hits dense material and glows brilliantly in X-rays for years to decades. The homunculus was effectively pre-built as the worst-case surrounding medium for a supernova threat calculation. The third factor is the rotational axis. The bipolar lobes of the homunculus extend along Eta Carinae's rotation axis. Measurements of the lobe orientation place the rotational axis at roughly 40 to 45 degrees from the plane of the sky, meaning it tilts somewhat toward Earth. In rapidly rotating massive stars that collapse to form black holes, gamma-ray burst jets fire along the rotational axis. If Eta Carinae's collapse produces a long-duration gamma-ray burst, those jets would fire in the general direction of our solar system. At 7,500 light-years, Eta Carinae sits near the distance threshold where a gamma-ray burst aimed directly at a planet could devastate its ozone layer. The alignment is not perfect, and the probability is not certain. The tilt means the jet would not point straight at Earth even if one forms, but the geometry is close enough that astronomers take it seriously. The timing is also unpredictable in a way. Betelgeuse is not. Betelgeuse appears to be progressing through defined nuclear burning stages that stellar models can track. Eta Carinae's luminous blue variable nature means it can undergo major outbursts without the kind of clear precursor signals that would allow advance warning. The Great Eruption of 1843 appeared with relatively little preparation visible in the historical record, a star getting brighter decade by decade. With a history of erupting without warning and a physical configuration that maximizes the danger of its eventual collapse, is a different kind of concern than a well-monitored dying giant several hundred light-years away. Before we can fully measure this threat, though, we need to understand a category of star that produces the most focused and lethal beams the universe makes. Because one of them, 8,000 light-years away, appeared until recently to be pointing straight at us. To understand what makes a gamma-ray burst so uniquely destructive compared to an ordinary supernova, you need to understand the kind of star that produces them. Most massive stars die surrounded by thick layers of hydrogen and helium they have held throughout their lives. When they collapse, the explosion fights outward through those layers, loses energy in the process, and emerges as a roughly spherical blast spreading in all directions. The energy is enormous, but it dilutes with the square of distance as it spreads, and it reaches nearby planets from every direction more or less equally. Wolf-Rayet stars are different in one critical way. They have already shed their outer layers entirely. These are stars that started at somewhere above 20 to 40 times the mass of our star, burned ferociously hot from the beginning, and drove stellar winds moving at thousands of kilometers per second, fast enough to strip away their hydrogen envelopes over millions of years. What remains by the time a Wolf-Rayet star approaches the end of its life is the raw nuclear core directly exposed to space. No hydrogen envelope, no thick outer buffer, just the blazing, carbon-rich or nitrogen-rich interior of a dying massive star losing mass at a rate 10,000 times faster than an ordinary star, radiating at surface temperatures of 25,000 to 50,000 Kelvin or more. Wolf-Rayet stars glow blue-white and fierce in visible light, and their spectra look unlike almost any other stellar type because the broad emission lines produced by their enormous, fast stellar winds overpower the absorption features that identify most stars. Their luminosities are extreme, hundreds of thousands to millions of times our star's output. They are rare because the stars massive enough to become Wolf-Rayet objects are rare in the first place and live short lives, but they are scattered throughout the Milky Way, burning brilliantly for the few 100,000 years they last before collapsing. The significance for gamma-ray bursts lies in rotation. Some Wolf-Rayet stars, particularly those in close binary systems where tidal forces have kept them spinning rapidly, retain high rotation rates as they approach core collapse. When the core of a rapidly rotating Wolf-Rayet star collapses, it can form a black hole surrounded by a rapidly spinning disk of infalling material. Energy extracted from the rotation of that system through magnetic field mechanisms can launch a pair of narrow jets in opposite directions along the rotation axis. These jets carry a significant fraction of the supernova's total energy, focused into a beam with an opening angle of only a few degrees. The difference in effective energy delivery between a sphere and a narrow beam is enormous. The same total energy, focused into a few degrees of angle rather than spread across an entire sphere, produces an intensity inside the beam that is orders of magnitude higher than the equivalent spherical explosion at the same distance. A gamma-ray burst that would be undetectable from a given location if its energy was spread uniformly becomes one of the most energetic events ever recorded if the beam happens to point directly at you. This is why geometry matters so profoundly in gamma-ray burst threat assessments. An explosion happening 1,000 light-years away, with its jets aimed elsewhere, is essentially harmless. The same explosion with a jet pointed directly at Earth is a calculation of a completely different kind. In 1999, astronomers imaging a Wolf-Rayet binary system 8,000 light-years away found something in its geometry that demanded immediate attention and gave the system a nickname that has followed it ever since: Peter Tuthill did not set out to find a death threat when he pointed the Keck telescope at a Wolf-Rayet binary system in Sagittarius in 1999. He was studying the dust production in the stellar wind collision zone between two stars and expected to find something technically interesting. What he found instead was one of the most photographed structures in infrared astronomy, and within weeks of the image becoming public, the popular press had given the system a nickname that has never left it. The two stars, in what is formally known as Wolf-Rayet 104, orbit each other every 220 days, slightly less than 8 months. As they orbit, the stellar winds from the Wolf-Rayet component and its companion collide in the space between them. In the compressed, cooling region where those winds meet, conditions are just right for hydrocarbon dust to condense from gas into solid particles. As the two stars orbit, this dust production zone sweeps in a circle, and the freshly formed dust spirals outward. The result, seen in infrared light, is a rotating pinwheel, an elegant logarithmic spiral stretching outward more than 200 astronomical units, wider than the distance across most planetary systems. When Tuthill's images were processed, the pinwheel appeared almost perfectly face-on. It looked exactly as you would expect if you were positioned almost directly above the system, looking straight down at a spinning spiral. The image was beautiful. The implication it carried was immediate and unsettling. If the dust pinwheel is face-on, the plane in which the dust spreads outward is nearly perpendicular to our line of sight. If the dust spreads in the orbital plane of the two stars, then the orbital plane is also nearly perpendicular to our line of sight from Earth. And if the orbital plane is perpendicular to our line of sight, then the poles of the Wolf-Rayet star, the direction any gamma-ray burst jets would fire, point approximately toward Earth. Tuthill stated it directly in a published paper. The geometry gave Earth an approximately pole-on view of a nearby, massive Wolf-Rayet binary. The system had been catalogued for years, and nobody had thought about what a face-on dust spiral implied about which direction the star's poles were pointing. Once the connection was made, the system received its popular nickname immediately: the Death Star. At 8,000 light-years, Wolf-Rayet 104 sits near the edge of the calculated danger zone for a gamma-ray burst aimed at Earth. The standard calculation places the threshold for serious ozone damage at roughly 6,500 light-years for a long-duration burst fired directly at a planet. Wolf-Rayet 104 is farther than that, but not enormously so, and the uncertainties in both the distance estimate and the ozone damage calculation meant the system could not be immediately dismissed. Tuthill himself estimated the probability of a damaging event at roughly 1%, accounting for all the uncertainties about whether a gamma-ray burst would even form, whether the jet would truly aim at Earth, and whether the distance was sufficient to dilute the energy below harmful levels. For years after the initial publication, Wolf-Rayet 104 carried its grim nickname through popular science writing. The geometry was striking, the physics was real, and the uncertainty was genuine. Then, in 2024, a follow-up study significantly changed the picture. But it did not change it completely, and what the new measurements revealed about the system, beyond the revised threat assessment, was a physical mystery nobody expected to find. Grant Hill arrived at Keck Observatory with a simple project in mind. He wanted to study the collision of stellar winds inside the Wolf-Rayet 104 system, particularly the X-ray bright zone where the Wolf-Rayet star and its companion traded material across the space between them. He assumed the orbit was face-on, because the dust pinwheel image Tuthill had published a quarter-century earlier looked perfectly flat against the sky. That assumption seemed so obvious it barely needed stating. When you look at a spinning pinwheel that appears flat against the sky, it is reasonable to conclude that whatever is generating, it must be oriented the same way. So Hill built his analysis around a face-on orbit and started measuring, using 3 separate spectrometers on the Keck telescope. He extracted radial velocity data for both stars. Radial velocity measures how fast an object is moving toward or away from the observer. In a truly face-on orbit, that signal is small or absent. A large signal indicates the orbit has a real tilt, with the stars spending a meaningful fraction of each cycle moving toward or away from Earth. The data came back showing a large radial velocity signal. The orbital plane of Wolf-Rayet 104 is tilted at least 30 to 40 degrees away from face-on. The two stars are not orbiting in a flat plane perpendicular to our line of sight. They are tilted significantly, and a tilt of 30 to 40 degrees in the orbital plane means the poles of the stars, the directions any gamma-ray burst jets would fire, are tilted the same amount away from pointing at Earth. The typical opening angle of a long-duration gamma-ray burst jet spans roughly 2 to 20 degrees of arc in total. If the poles are tilted 30 to 40 degrees away from our direction, we fall well outside even the widest jets produced by stellar collapses. The Death Star, it turns out, is almost certainly not aimed at Earth. Hill described what he found with the exact surprise it warranted. He had begun expecting the orbit to match the pinwheel, had assumed both were telling the same story, and found instead they were telling different ones. The pinwheel looked face-on. The orbit was not. Something in the mechanism that creates the dust spiral, the way compressed stellar wind cools into solid particles and sweeps outward as the star's orbit, was operating in a direction that did not match the orbital geometry driving it. Nobody knows why. The standard model of colliding wind dust spirals assumes the dust travels outward along the orbital plane. If the orbital plane is tilted, but the spiral appears flat, then the dust is not following the rules the model prescribes. The system is a physics problem with no current solution, and the researchers who know it best have spent considerable time asking what they are missing. The threat assessment dropped dramatically, but the probability of danger did not reach zero. There is still real uncertainty in the exact distance, in whether the Wolf-Rayet component would produce a gamma-ray burst or a more standard supernova, and in the precise geometry of any jet that might form. A roughly 1 in 100 chance at 8,000 light-years is not a crisis. The universe contains far more dangerous stellar objects than a system whose best evidence now points away from us. Those more dangerous objects operate on physics more extreme than anything inside Wolf-Rayet 100. 4. The most extreme of all is an object so small you could drive across it in half an hour. Yet it already reached across 50,000 light-years and physically changed Earth's atmosphere. When a massive star's core collapses and the dust settles in the seconds afterward, what remains is already one of the most extreme objects in the observable universe. A sphere about 30 kilometers across, containing the mass of our star compressed beyond any ordinary matter, with a solid crystalline crust and a fluid of subatomic particles churning inside. Each teaspoon of its material outweighs a mountain range. A spoonful dropped on the surface of Earth would fall straight through the planet. This is a neutron star, and it is already far beyond anything physics produces through ordinary means. All neutron stars are magnetic. The collapse of a spinning star, combined with the amplification of the original magnetic field during compression, leaves every neutron star with a powerful magnetic field. Most have fields around 1 trillion Gauss, roughly 1,000 billion times stronger than Earth's own magnetic field, strong enough to strip electrons from atoms at distances of several kilometers. For decades, astronomers classified these objects and moved on, treating their magnetic fields as large but manageable parameters in the physics of dense matter. Then they found the outliers. Roughly 10% of all neutron star births produce something beyond the standard category. The magnetic field, instead of stopping at 1 trillion Gauss, reaches 10 to the power of 15 Gauss, a quadrillion Gauss, 1,000 times stronger still. At this field strength, atomic physics ceases to function in any recognizable way. Hydrogen atoms, normally spherical shells of electron probability surrounding a proton, are compressed by the field into needle-like shapes elongated along the field lines, hundreds of times longer in the field direction than across it. Electrons are stripped from atoms at distances of thousands of kilometers simply by proximity, and the vacuum of space itself begins to behave in ways that require quantum electrodynamics, the deepest theory of light and matter, to describe. This last effect is the strangest. A magnetic field strong enough to modify the quantum behavior of empty space is called vacuum birefringence. In ordinary space, light travels through the vacuum at the same speed, regardless of its polarization. In the magnetic field of a magnetar, polarization modes of light travel at slightly different speeds because the field itself distorts the quantum structure of the vacuum. This is a direct prediction of quantum electrodynamics that exists nowhere else in the universe, close enough for us to test directly. Magnetars make physics stranger than most laboratory experiments can reach. The energy source is different from everything else in the sky. Stars burn nuclear fuel. Pulsars radiate by slowing their spin over millions of years. Magnetars are powered by the gradual decay of their own magnetic field. As that field weakens over thousands of years, the stored magnetic energy converts into radiation, releasing heat and X-rays without any fusion required. The energy stored in a magnetar's field is staggering. You can calculate it from field strength and volume, and the result is an energy reservoir that dwarfs what most stars emit in millions of years of ordinary operation. The field holds that energy in a kind of magnetic tension, compressed into an object 30 kilometers across, waiting for something to trigger its release. What triggers it is structural. The crust of the magnetar is under enormous stress from the field lines threading through it, and occasionally that stress finds a crack. What happens when the crust cracks is something that redefines the word violent, and the energy it releases can travel across most of a galaxy and still change the atmosphere of a planet that never knew it was in range. The crust of a magnetar is not soft or fluid. It is a solid crystalline lattice of atomic nuclei, compressed to densities far beyond anything produced in a laboratory, threaded through by magnetic field lines so powerful they exert enormous mechanical stress on the material they pass through. The crust does not give way easily, but given enough time and enough accumulated stress, even the hardest material breaks. When the magnetar's crust cracks, the consequences unfold faster than almost any other physical event in the universe. The crack itself is a starquake, the stellar equivalent of an earthquake, but the comparison is inadequate in almost every way. The largest earthquake ever recorded, the 1960 Valdivia event in Chile, released roughly 10 to the power of 18 joules of energy. That number is large by human standards, large enough to shift coastal geography and send tsunamis across an ocean. A magnetar starquake releases 10 to the power of 47 joules in fractions of a second. This is not a larger earthquake. It is a categorically different class of event. When the crust shifts, the magnetic field lines anchored to it suddenly find themselves in a new geometry. Field lines that were under tension are now in the wrong positions relative to each other. In a process analogous to magnetic field reconnection in solar flares, but operating at energies millions of trillions of times higher, the field lines rearrange in a massive topological event, releasing stored magnetic energy explosively. The energy emerges as an expanding fireball of electrons, positrons, and extremely energetic photons, a trapped magnetic cloud growing outward from the magnetar's surface faster than any ordinary explosion. This fireball does not spread uniformly. The magnetar is spinning, completing full rotations every few seconds. As it rotates, the scar on the magnetar's crust where the quake occurred sweeps in and out of our line of sight. The energy arriving at a distant observer pulsates at the magnetar's rotation period, encoding the spin rate of the object directly into the burst signal. This oscillation in the arriving radiation is one of the clearest signatures of a magnetar event, and it allows researchers to identify the spinning scarred crust as the source even from across the galaxy. The fireball itself is followed by a sustained pulsating tail, as the magnetar continues to shine brightly for minutes after the initial peak, gradually fading as the stored energy radiates away. The total energy in the entire event, initial spike plus pulsating tail, represents only a small fraction of the total magnetic energy stored in the field. The field continues to exist. It will stress the crust again. Magnetars are not one-time events. They repeat, firing bursts of varying intensity throughout their active lifetime, which lasts roughly 10,000 years before the field decays to the point where the crust is no longer under enough stress to crack catastrophically. For most of the known magnetars, the bursts are powerful enough to be detected by space observatories, but too distant to affect Earth directly. The events are logged, analyzed, and filed into the growing catalogue of magnetar behavior that researchers use to build models of how these objects work. Then, on December 27th of 2004, a magnetar on the other side of the Milky Way fired a burst of a different magnitude entirely, and the detectors that registered it were not the ones pointed at the right part of the sky. They were the ones pointed everywhere else, because when this event hit, it overwhelmed every instrument in orbit simultaneously, and it rewrote what astronomers thought was possible at 50,000 light-years. At 7:35 in the morning on December 27th, 2004, sensors aboard multiple satellites in orbit around Earth registered something they had not been designed to survive. The source was a magnetar designated the Magnetar, sitting 50,000 light-years from Earth in the constellation Sagittarius, on the far side of the Milky Way. The burst it released would become the single most energetic cosmic event ever recorded from beyond the solar system. In the initial 1/10 of a second, the magnetar released approximately 4 times 10 to the power of 46 joules of energy. To put that in a frame of reference that stays with you, this is more energy than our star radiates in roughly 250,000 years, released in less time than it takes to blink. The gamma-ray spike that followed this was so bright that it saturated every gamma-ray detector in orbit that caught the event, including instruments on the space agency's Swift satellite, which had been designed to measure gamma-ray bursts from billions of light-years away. Bursts so distant that the detector was calibrated for the faintest possible signals. The burst from the magnetar, 50,000 light-years away and a fraction of the distance Swift was designed to handle, hit every detector so hard the instruments registered their maximum measurable value and stopped. Swift was not even pointed in the direction of the burst. The radiation passed through the satellite's walls and overwhelmed the detectors regardless of their orientation. The same happened to the orbiting gamma-ray telescope, to the Reuven-Ramati high-energy solar spectroscopic imager, and to other satellites in orbit that happened to be on the day side of Earth at the time. Every instrument capable of detecting high-energy radiation saw a uniform saturation event. The effects on Earth were direct and measurable. The ionosphere, the electrically charged layer of atmosphere extending from roughly 60 to 600 kilometers altitude, is normally maintained in its daytime state by ultraviolet radiation from our star. At night, with no incoming solar radiation, the ionosphere recedes and its nighttime chemistry takes over. The magnetar burst arrived while it was nighttime for large portions of Earth. In seconds, it converted the nightside ionosphere to daytime conditions. The radiation from a dead star's cracked crust, 50,000 light-years away, produced as much ionizing energy in Earth's upper atmosphere as the star we orbit produces during a full day. Radio communications in the affected regions were disrupted. The geomagnetic field was measurably compressed by the arriving radiation. Above the atmosphere, some satellites shut down their sensitive electronics as a precaution against the particle flux. In the Arctic, observers reported sudden auroras appearing without warning at the moment the burst arrived. The pulsating tail of the event lasted approximately 380 seconds, oscillating with the magnetar's rotation period of about 7.56 seconds, each pulse sweeping through our detectors as the magnetar's scar rotated into view. The event continued for more than 6 minutes. If the magnetar had been located within 10 light-years of Earth when it fired this burst, calculations suggest the ozone layer would have been destroyed globally. What reached Earth from 50,000 light-years was only a tiny fraction of the burst's total energy. The inverse square law attenuated the radiation enormously with distance. At 10 light-years, essentially nothing would have survived on the surface. And here is the detail that researchers noted quietly in the papers that followed. There may be magnetars far closer that we simply have not found yet. There are roughly 30 known magnetars in the Milky Way. The number is small, and part of the reason is physical. Magnetars are born young. The extraordinary magnetic field that defines them begins decaying the moment the magnetar forms, losing strength over roughly 10,000 years. After that timescale, the field has weakened to the point where the crust no longer breaks under its stress. The burst activity stops, and the object becomes what most neutron stars are: a spinning, cooling remnant, still extraordinary by ordinary standards, but no longer distinguishable from the vast population of ordinary neutron stars in the galaxy. 10,000 years sounds long, but it is brief compared to stellar timescales. Our galaxy is roughly 13 billion years old. In those 13 billion years, it has produced somewhere between 100 million and 1 billion neutron stars from the deaths of massive stars. If roughly 10% of those births created magnetars, and if each magnetar phase lasts about 10,000 years, the number of active magnetars at any given moment is only a few hundred in a galaxy of hundreds of billions of stars. Finding even 30 of them requires looking specifically for their X-ray and gamma-ray emission, and doing that successfully depends on having the right instruments pointed at the right parts of the sky. The inner regions of the Milky Way, where the star density is highest and most neutron stars are produced, are also the most heavily obscured by gas and dust. Radio waves penetrate this dust, which is why we know a great deal about the pulsar population in the galactic center. High-energy X-rays penetrate it as well, but detecting a magnetar in quiescence, when it is not actively bursting, requires sensitivity that current X-ray telescopes can only achieve for the nearest and brightest examples. The dusty interior of the galaxy hides enormous numbers of stellar remnants, and how many of those include active magnetars is genuinely unknown. Estimates of the total number of magnetars that have existed over the galaxy's history reach into the millions. Most are now silent, their fields decayed, their crust activity finished. But the ones active right now, the ones undergoing starquakes and releasing bursts, are distributed throughout a galaxy we cannot fully see. The nearest known magnetar is roughly 9,000 light-years from Earth. That distance is comfortable by the standards of the December 2004 event, which came from 50,000 light-years and still changed the ionosphere. A magnetar 9,000 light-years away firing a comparable burst would deliver far more energy to Earth's atmosphere. The nearest unknown magnetar is a more unsettling question. There may be active magnetars at distances of a few thousand light-years that have simply not announced themselves yet with a large enough burst to be detected through the dusty spiral arm material between here and there. The galaxy is not transparent, and our catalogue of the objects it contains is incomplete. What this means is that the threat landscape from dangerous stars is real, ongoing, and incompletely mapped. The appropriate response is listening. Humanity spent most of its history watching the sky with no idea what stars were, let alone what they could do. For the first time in our existence, we built infrastructure designed specifically to hear the first signal from a stellar catastrophe before the damage arrives. That story begins with a single physical fact about the particle that travels fastest and carries the most warning. The advantage that neutrinos provide is not complicated. When a massive star's core collapses, two signals depart almost simultaneously. The first is neutrinos, which interact so weakly with matter that they pass through the entire star as if it were not there. They travel outward at the speed of light from the moment the core forms. The second is the shock wave, which takes a very different path. It forms at the surface of the collapsing core, then fights outward against the infalling material of the outer stellar layers, losing energy and time in the process. For a star the size of Betelgeuse, that journey through the outer layers takes somewhere between 15 and 25 minutes. For anyone watching a nearby supernova, this means the neutrinos arrive 15 to 25 minutes before any visible light. The star has not yet shown any sign of explosion on the sky. The neutrinos have already traveled across the star, through the outer layers without slowing, across the distance between the star and Earth, and are already arriving at detectors underground. The explosion has begun. The light has not reached us yet. This gap is not a curiosity. It is a warning window. In 15 to 25 minutes, observatories across the world can slew their telescopes to the right position, prepare detectors, lock in recording systems, and capture the very first photons of a nearby stellar explosion rather than missing the critical early data. For Betelgeuse specifically, neutrino physicists have estimated that with current detectors, this warning would provide enough lead time to capture the shock breakout, the brief, intense flash of radiation when the shock wave first breaks through the stellar surface, an event that lasts only minutes and is routinely missed in supernovae detected after the fact. In 1998, a collaboration of physicists and astronomers built a system specifically to catch this warning. The Supernova Early Warning System, which physicists call the Supernova Early Warning System, connected underground neutrino detectors across multiple countries into a single automated network. The logic was straightforward. Any single detector might register a false alarm from random background events. Two or more independent detectors registering coincident bursts within 10 seconds is a signature that is statistically impossible to explain by coincidence. When that happens, the warning system servers send an automated alert to every major observatory in the world. The alert arrives before the supernova is visible. The telescopes point, and when the first light comes, astronomers are already watching from the moment it arrives. The system has run in automated mode since 2005, with near-complete uptime and zero false alarms across more than 2 decades. That reliability was built in the coincidence requirement across multiple independent detectors, separated by thousands of kilometers and responding to completely different backgrounds, made accidental triggering essentially impossible. What the original system lacked was sensitivity to the period before the collapse itself. In the days and weeks before an iron core forms, a massive star in its silicon burning phase produces a measurable increase in neutrino flux without any dramatic visible change. A major upgrade extended the network and integrated gravitational wave observatories into the alert chain. The upgraded system, sometimes called the Warning System 2.0, added the capability to send early warnings based on elevated neutrino flux before any collapse has actually occurred. What the warning system needs most, beyond automated software, is detectors large enough to see anything, and the detectors that have been built for this purpose are among the most unusual structures humans have ever put underground. The largest neutrino detector on Earth is a cubic kilometer of Antarctic ice. IceCube is built into the glacier at the South Pole, instrumented with 5,160 optical sensors attached to cables that were drilled straight down through the ice to depths of up to 2.5 kilometers, then frozen in place when the drilling stopped. Each sensor waits for the rare flash of blue light that occurs when a neutrino interacts with the ice and produces a charged particle moving faster than light travels through that particular medium. The result is a cone of faint blue radiation called Cherenkov light, detectable by the sensors in the surrounding volume. For ordinary cosmic neutrinos from distant sources, IceCube looks for individual events, rare flashes of light that stand out against the detector background. For a galactic supernova, the approach is different. The neutrino flux from a nearby core collapse would be so intense that IceCube would register a global surge across every sensor in the array simultaneously, the entire detector's background rate jumping unmistakably for roughly 10 seconds. For a Betelgeuse supernova, calculations suggest IceCube would register millions of interactions spread across the detector in that window, providing a simultaneous confirmation of whatever Super Kamiokande sees underground in Japan. Super Kamiokande sits in a mineshaft under Mount Ikenoyama, holding 50,000 tons of ultra-pure water in a cylindrical tank lined with 13,000 photomultiplier tubes. For a Betelgeuse collapse, the detector is estimated to register somewhere between 8,000 and 24,000 individual neutrino interaction events, enough to reconstruct the neutrino emission profile in extraordinary detail, essentially watching the collapse unfold through its neutrino signal second by second. In the summer of 2020, the detector's operators dissolved gadolinium sulfate into the water, dramatically improving the ability to detect the neutron produced in each neutrino interaction and sharply reducing background noise. In space, SWIFT monitors the full sky for gamma-ray transients, capable of detecting the initial radiation burst from a stellar explosion within seconds and alerting ground-based telescopes to its position. The Fermi Gamma Ray Observatory carries an all-sky monitor that saw the first hint of high-energy emission from Eta Carinae's colliding winds, extending our knowledge of that violent system beyond visible wavelengths. Chandra X-ray Observatory tracks the long-term brightening of the 1987A remnant, watching a decades-old explosion's shockwave slam into its surrounding gas ring in real time. The James Webb Space Telescope, since beginning operations in 2022, has imaged massive stellar environments and supernova remnants at infrared wavelengths with sensitivity that was impossible before it flew. Hyper Kamiokande, a successor to Super Kamiokande with a volume more than 5 times larger, is under construction in Japan and is scheduled to begin operations in 2027. For a Betelgeuse supernova, Hyper Kamiokande would detect approximately 100,000 individual neutrino events, providing a dataset that would allow reconstruction of the collapse profile at unprecedented precision. Beyond underground detectors, satellites built for other purposes also contribute. The Transiting Exoplanet Survey satellite, designed to find exoplanets by watching for tiny brightness dips, monitors Betelgeuse continuously at minute-by-minute cadence. In January 2023, it caught a supernova shock breakout in real time, a detection impossible without continuous coverage, demonstrating the kind of sensitivity that will matter when the next nearby stellar death begins. All of these instruments are running now, continuously. The network they form is the most sophisticated early warning system ever built for any kind of cosmic event. And the most forward edge of what it can detect reaches deeper than the collapse itself, into the days before it. The warning window that most people imagine from a neutrino alert is the gap between the neutrino burst and the visible light, those 15 to 25 minutes before the sky changes. That is real and valuable. But researchers working on the problem of pre-supernova detection have been chasing a longer window, one that begins not at the moment of collapse, but in the days or weeks before it. The physics that opens this window comes from the nuclear burning stages leading up to core collapse. Silicon burning, the final stage before the iron core forms, produces neutrinos at a rate significantly higher than earlier burning stages. These are thermal neutrinos produced by the extreme heat and density in the burning shell, and they carry energy directly out of the star without interacting with the surrounding material. As silicon burning advances, the neutrino flux streaming outward from the star increases. It is still far below what the collapse itself will release, but it is higher than the background that Super Kamiokande and other detectors see from Betelgeuse in its current state. Scientists at Super Kamiokande have published analyses suggesting the detector could register the elevated pre-supernova neutrino flux from Betelgeuse as early as 48 hours before the core collapse occurs. 48 hours is enough time to alert every observatory in the world, to schedule continuous coverage, to prepare the neutrino detectors themselves for the main burst, and to communicate the situation to institutions that maintain records of stellar events. It does not allow evacuation or intervention. Stars do not take requests. But it changes what science can learn from the event dramatically. Beyond neutrinos, some pre-supernova stars have shown detectable changes in behavior in the period before their collapse. The supernova designated 2020T, LF, was observed to have clear evidence of violent mass ejection in the surrounding medium in the 100 days before the visible explosion. Material had been blown off the star in large quantities shortly before the core collapsed, and the supernova shockwave plowed into this recently ejected material brightly enough to confirm that something had changed in the star before the end. Astronomers watching that system might have noticed the mass ejection in real time, given the right monitoring. Whether Betelgeuse shows similar precursor behavior before its eventual collapse is unknown. The Great Dimming of 2019 was a mass ejection event, but it was not a pre-supernova signal based on every line of analysis that followed. The nuclear burning stages that would precede collapse are occurring in the core, invisible to optical or infrared telescopes. Only the neutrino flux would carry that information outward. What the combination of all these detection strategies creates is a layered warning system with multiple possible inputs. A weeks-long neutrino flux increase, a potential mass ejection visible through telescopes, then the 15 to 25-minute neutrino burst window before the visible explosion. Each layer adds information and lead time. The system is imperfect, uncertain, and not yet tested on a real nearby supernova. But no generation of humans before this one had any of these layers available. The last time a star exploded close enough to see with the naked eye, nobody alive in the world had the slightest idea what they were looking at. They watched something extraordinary appear in the sky and had no way to know what had produced it or what the object had been. They simply called it a new star and kept watching until it faded. In the year 1006, observers across 4 continents recorded the appearance of a new star in the southern constellation Lupus. The accounts that survive come from China, Japan, Egypt, Iraq, and Europe. They agree on the essential facts. A point of light appeared in a part of the sky where no star of comparable brightness had been, and it was extraordinary. At its peak, this new star reached an apparent magnitude of roughly -7.5, making it brighter than Venus, brighter than anything in the night sky except the moon. It cast shadows after sunset. On good nights, literate observers wrote by its light. It remained visible to the naked eye for more than 2.5 years before fading completely. The star was roughly 7,000 to 8,000 light-years away. Its explosion was a real event. A massive stellar collapse scattering heavy elements into the surrounding interstellar medium, leaving behind a neutron star or black hole at its center, sending cosmic rays outward in all directions. None of the people recording it knew any of this. They watched a new light appear, brighten, hold, and fade, and they had no framework to explain what kind of object produces this behavior. 48 years later, in the summer of 1054, another new star appeared, this time in Taurus. Chinese astronomical records document it extensively. Some Japanese records reference it. Arab chronicles from the period include descriptions. It reached an apparent magnitude of roughly -3 to -5, comparable to Venus or brighter, and was visible in daylight for 23 days. It remained visible to the naked eye for roughly 21 months. The remnant of that explosion is now the Crab Nebula, one of the most studied objects in the sky. At its center spins a pulsar, the neutron star left behind after the core collapse, rotating 30 times every second and radiating X-rays detectable from Earth. 1,000 years after the explosion, the neutron star formed in its core is still visible and still being measured. In 1572, a new star appeared in Cassiopeia, and the Danish astronomer Tycho Brahe measured it carefully. He found it showed no parallax shift relative to the background stars as Earth moved through its orbit, which meant the object was far beyond the Moon, in the realm the ancient Greek model of the universe called perfect and unchanging. A new star appearing and fading in the domain that was supposed to be eternal and fixed was a philosophical problem as much as an astronomical one. Tycho's measurements forced a confrontation with the assumption that the heavens did not change. In 1604, the last naked-eye supernova in the Milky Way appeared in Ophiuchus, roughly 20,000 light-years away. Johannes Kepler observed it carefully and published an entire book about it. It was visible for roughly a year. No human alive today has watched a star explode in our own galaxy with their own eyes. The gap since Kepler's supernova has extended to more than 420 years. Statistically, a gap this long is uncommon. The galaxy has been producing these events throughout that entire period, but accidents of position and dust have hidden them from view. The ending of this drought is a question of when, not whether. When it ends, the population of people watching the sky with instruments will be incomparably better prepared than any of the observers who recorded the previous events. The reason they will be prepared leads back to one specific atom, forged in violence, present in everything alive. Every atom heavier than hydrogen and helium in the observable universe was made inside a star. This is a statement worth sitting with, because it has implications that reach into every material thing that exists. The carbon in every organic molecule on Earth, including every molecule in every cell of every living thing that has ever existed on this planet, came from a stellar interior. The oxygen in water, the silicon in rock, the calcium in bone, the iron in blood, the gold in jewelry, the uranium in reactor fuel, all of it forged inside stars, massive enough to burn through the necessary nuclear fuel and then explosive enough to scatter the results across space. The universe that emerged from the first moments after the beginning contained almost exclusively hydrogen and helium, with trace amounts of lithium. Every other element in the periodic table required a star to make it. The process of making these elements, stellar nucleosynthesis, is not metaphorical. It is the literal mechanism by which the matter composing living creatures was assembled from simpler material over billions of years and multiple stellar generations. A star like Betelgeuse, burning its way through hydrogen, helium, carbon, neon, oxygen, and silicon in its concentric burning shells, is manufacturing elements through each of those phases. When it explodes, the shockwave tears through those shells, and the explosion itself drives additional nuclear reactions, creating new isotopes in the intense heat and pressure of the expanding blast. The material from all of those shells scatters outward into the surrounding interstellar medium at roughly 10% the speed of light. Over millions of years, that material mixes with the surrounding gas and dust. Gravity draws the enriched cloud together, and if the density is right, the cloud collapses into a new star and its surrounding disk of material. Planets form in that disk, built from the elements scattered by previous stellar generations. Life, if it emerges on any of those planets, is built from atoms that carry this history inside them. The carbon bonding in every organic molecule links back to a helium flash in a stellar interior billions of years ago. The iron carrying oxygen in blood was forged in the silicon-burning shell of a star that died before our solar system existed. The atomic evidence of this cycle is confirmed directly. Iron-60 in oceanic crust from 2 to 3 million years ago is real supernova fallout, preserved in geological layers. The gold spectral lines in the kilonova of 2017 confirmed that neutron star mergers produce heavy elements through rapid neutron capture, extending the roster of confirmed nucleosynthesis sites beyond supernovae. What this means for the story of dangerous stars is more than context. The violence is not incidental to life. It is the upstream condition for it. The molecular cloud that collapsed to form our solar system was enriched with heavy elements by at least one previous supernova, and probably several over the 4.5 billion years of Earth's existence. Every atom heavier than iron that makes complex chemistry and biology possible required an event comparable to what killed those stars. The explosions that could in principle threaten the ozone layer of a planet are the same category of event that built the chemistry available to that planet in the first place. This is the deepest loop in the story. The universe is not indifferent to life in the sense of being hostile to it. It produced life by being the kind of place where stars explode, and when the next nearby star collapses, we will know it is coming before anyone can see it in the sky. The honest answer to the question this story has been building toward is that we cannot predict precisely when the next stellar catastrophe will occur, or exactly which star will produce it. Betelgeuse carries a companion now named Betelbuddy, orbiting inside its own atmosphere. And the presence of that companion changes every model of how the final collapse will proceed. Eta Carinae is a luminous blue variable that erupted with massive force in 1843 without giving observers any reliable warning, and its next major outburst, whether a lesser eruption or its final collapse, carries the same unpredictability. Wolf-Rayet 104 is probably aimed away from us, but probably is doing real work in that sentence. Magnetars exist in numbers we cannot fully count, in positions we cannot fully map, inside a dusty galaxy that hides its contents. The uncertainty is genuine, and it is not going away. No instrument we have built can look inside a stellar core and read out the exact number of years remaining in each burning stage. No algorithm currently predicts which convective instability in Betelgeuse's outer atmosphere will be the one that immediately precedes collapse, or whether the companion's gravitational stirring during its orbital passage will accelerate or delay the end. The universe does not provide these answers on request. What it does provide is neutrinos. Neutrinos arrive before the light. They pass through the outer stellar layers while the shockwave is still fighting its way toward the surface. They travel at the speed of light across whatever distance separates the dying star from Earth, carrying the precise timestamp of the collapse event, arriving at underground detectors in time for the people watching those detectors to turn every telescope in the world toward the right position in the sky before the first photon of the explosion has arrived. For 420 years, no star in the Milky Way has exploded close enough to see without a telescope. The observers who watched the previous events had instruments extraordinary for their time. They had no way to know what they were seeing. They had no way to hear it coming. We built that. Starting in 1998, the network of neutrino detectors that became the warning system was connected, tested, upgraded, and extended across continents. Every instrument from Super Kamiokande in Japan to IceCube at the South Pole contributes a piece of the coincidence network, and any two of them triggering together within 10 seconds sends an automated alert to every major telescope and observatory in the world before the explosion has shown itself visibly. Betelgeuse still burns in the shoulder of Orion. Every winter, the faint reddish point marking the hunter's arm for as long as people have looked up and wondered, it is in the final stages of its nuclear life, burning through whatever fuel remains with the patience of a star and the urgency of a clock. Betelbuddy orbits inside its atmosphere on a 6-year path, gravitationally stirring the outer layers with every passage, possibly reshaping the conditions of the eventual collapse in ways the models are still working to capture. Somewhere underground, the detectors are running. The sensors are counting. The network is waiting for the specific pulse of particles that can only come from one thing. When Betelgeuse finally goes, we will hear it before we see it. In that window between the neutrino burst and the first light, the machines will speak first, and across the night sky, in the place where a red star marked the shoulder of the hunter, a new light will arrive. We built ears for this. They have been listening for years.